In the previous modules, we have discussed the classification problems when we had two groups or two populations. We had been looking at the expected cost of misclassification and the total probability of misclassification to classify the individuals into one of these two groups. Later on, we saw that the two groups may be identified by normal populations. So, we had two normal populations and we were trying to classify individuals into one of these two normal populations. What we will do in today's lecture is to extend this classification rule to more than two populations. So, what do you do if we have say 10 or 15 different populations and we want to put one individual into one of these 10 or 15 groups? How do you build up a classification rule for this? We will again be using the total probability of misclassification or the expected cost of misclassification as the general rule. So, let us look at the problem of classifying an individual when we have more than two classes. So, we have m characteristics of an individual given by the vector x running from x1, x2 to xm. We assume that there are R groups. Of course, R is greater than 2, 2 would be a special case for R, and Gk is the kth group, which is characterized by the probability function fkx. The prior probability of belonging to the kth group is pk, and of course, summation of pk over all k would be equal to 1. The misclassification costs are assumed to be Ck given j, which is the cost of allocating to Gk, that is to the kth group, an individual who actually belongs to the jth group. So, our problem now is to find a rule by which an individual can be identified with one of the groups Gk. So, we will base our rule on the misclassification probabilities. Let omega be the sample space, that is the space of all possible values of x. We will partition omega into mutually exclusive and exhaustive subsets Rk. There will be R such partitioned space, and we will then set up a rule that if x belongs to Rk, we assign it to the kth group Gk. In that case, the conditional probability of misclassifying an individual coming from the jth group Gj to the kth group Gk is probability of k given j, that is probability x belongs to Rk given Gj. X belongs to Rk means we have assigned him into the kth group, and given Gj means the individual comes from the jth group. This is given by the integral of fjx dx over Rk, because fjx is the probability function under the jth group, and you are now in the region for the kth group. So, it will be integrated over Rk. Note that the correct classification in this case is now 1 minus summation over k not equal to j, probability of k given j, because if you look at all the other k's which are not equal to j, those are the misclassification probabilities. So, that the sum would give the misclassification probability, and 1 minus that would be the correct classification probability. Let us look at the expected cost of misclassification. The expected cost of misclassifying an individual from the jth group to any other group would be ECM, we will write it as ECMJ, which is cost of misclassification into the first group given that he comes from the jth group, into the probability of misclassification into the first group given that he comes from the jth group. And this would be summed for all k except when k is equal to j. So, we get this as a sum of the cost into the probability of misclassification. Now, the ultimate expected cost of misclassification over all groups would be ECM, which is P1 into ECM1, etc. up to PR into ECMR. This is because we look at P1 is the probability of coming from the first group, and ECM1 is the probability or the expected cost of misclassification of an individual coming from the first group. Similarly, PR is the probability of coming from the RL group, and ECMR is the expected cost of misclassification of such an individual. So this sum actually gives us the expected cost of misclassification. Then the optimal rule is choose RKs such that the ECM is minimized. So we want the expected cost of misclassification to be as small as possible. Now for the classification rule, the region determined by allocating X to a group Gj such that the sum of this Pk into Fkx into Ck given J summed over K up to R except for J, we want this sum to be minimized. This can be mathematically shown, and you will see that in the text, but what we can see here is that if you look at Pk, small pk is the probability of the prior probability of the individual coming from the kth group, and Fkx and Ck given J are the probability function and the cost for misclassification. So overall, this actually, the whole thing gives you the probability that an individual coming from the jth group is classified into the kth group, and you actually sum this over all k and you get this, and if this is minimum, then this gives you the best allocation of X into the jth group. If you have a tie, then X may be allocated to any of the tied groups. So if there are two groups in the second and the fourth group which has the same minimum value, then you can allocate X to either one of these two groups. Let us look at an example. Now consider three groups, and we will be looking at the following data, and the problem is to allocate an individual A who has a characteristic X to one of the groups. Now what we have in this table is that for the columns we have the two true groups and the rows are the allocated groups. So if you look at the top, you have G1, G2, G3, these are the actual groups in which the individual belongs, and the allocated groups are the G1, G2, G3 that he has been put into on the basis of the classification rule. You see that the diagonals are 0 because the cost of correctly classifying is 0, and then you have the cost 10, which is the cost of classifying an individual from the second group into the first group. Similarly, 20 is the cost of classifying an individual from the third to the first group. So this is the first 9 observations that we have. Then we have the prior probabilities for each of the groups. So an individual coming from the first group has a chance of 0.4. So the probability of an individual coming from the second group is 0.25 and from the third is 0.35, and you can see that this sums up to 1. Fx is the value of the ordinate at x. So x is the characteristic of A, and the value that it takes in the first group is 0.62, from the second group it's 0.34, and from the third group it's 0.42. Of course, it will depend on what type of function fx is. Now if you look at this, then when we compute this pk into fkx into ck given j, for the first group G1 we have pk is the probability of coming from that group, which is 0.25. This is the probability actually from coming from the second group, and 0.34 is the ordinate of x in the second group. So it's f of 2x and 10 is the cost. Similarly, 0.35 is the probability of coming from the third group into its ordinate at x and into the cost of misclassification. So if j is equal to 1, then we have this sum over the second and the third components, and this comes out to be 3.79. Similarly, for G2 we can do the same thing and the value comes out to be 3.45, while for G3 the value comes out to be 7.22. And now we can see that the minimum is 3.45, which coincides with the second group. Therefore, we allocate A to the second group. That is how the rule works. So we compute this component Pk, Fk into C for each of the three groups where the particular group itself is missing. So these are the misclassifications, and then we minimize this misclassification cost and then allocate G2 or A to the corresponding group. There is another way of looking at this which is slightly simpler, and this is referred to as the total probability of misclassification. This assumes that the cost of misclassification is equal for all the groups. So if it's equal for all the groups, then it can be taken as a constant, and this constant actually negates each other, so we need not bother about this constant anymore. And if we do that, then we only need to minimize Pk into Fkx, because C is now constant and we can rule that constant out. This is of course smallest when the omitted term is the largest. Why do you say that? This is because if you take k equal to 1 to r including j, so what we are minimizing is k equal to 1 to r excluding j, so that will be including j minus the jth one, that is minus pj into fjx. And because if you are taking over all of the k equal to 1 to r, that would cancel out for different j's, and it will just be a choice between the pj into fjx. So the minimum would come out as the largest of these values because you have a negative sign. So the rule can be simplified to allocate x to gj if pj fjx is greater than pk fkx for all k not equal to j. What happens to our example? We say that the same problem now becomes much simpler. So we need to just calculate for G1 the probability of coming from G1 into the ordinate at x for G1, which is 0.62, and we get the value is 0.248. Similarly for G2 we get this is 0.085, and for G3 we get this value as 0.147. And now we see that the maximum is for G1, which is 0.248, and hence we allocate A to G1. Now how do you decide on which of the measures is good, which of the classification rule is good? So we need for a performance measure which does not depend on the form of the parent population. Mind you, we have looked at other performance measures, but they actually depended on the underlying distribution of the parent population. In this case, we look at a slightly different performance measure. Now suppose there are nk observations from gk, and we will denote by nkkc, there is the number of correct classification of individuals. So kk actually means that we have an individual from group k who is classified into group k, and C stands for correct classification. As opposed to this, we have nkjm, where we have a misclassification of individual from the kth group to the jth group, and m in this case stands for misclassification. So nkkc are the correctly classified individuals, and nkm KJM are the misclassified individuals. So if we have a sample like this, we can build what is referred to as a confusion matrix, and it will look something like this. So you again have the predicted membership and the actual membership. So the first row actually gives you actual membership is G1 and the predicted membership is G1 or G2 or GR, and you can see that the diagonals are always going to come out as NJJC because these are the correct classification. Given this confusion matrix, we can define the apparent error rate as APER is sum over K and J, NKJM, K and J are not equal, divided by summation of NK. Now if you look at the denominator, this is simply the size of the sample, and if you look at the numerator, this is simply the number of misclassified individuals. So the apparent error rate is the ratio of the number of misclassified individuals to the total number of individuals in the sample, and this gives you a very good idea of whether the rule is good enough or not. The larger this value is, means that you have more misclassification and the rule is not good, and the lower this value is, which means that the numerator is small, and you know that in that case you have correctly classified most of the individuals. So this gives you a very good idea of how good the classification rule is. Let us look at a special case for the normal populations. Now before we had assumed that GJ had the general form of the probability function Fjx. Now if Fjx has the normal distribution, that is x follows normal mu j sigma j, then we have the usual normal probability function under the jth group. So this is 1 by twice pi to the power of m by 2 sigma j to the power of half, and you have exp, that is the exponent, to the power of minus half x minus mu j prime sigma j inverse x minus mu j. And if we assume that the cost of misclassification is the same, which we can without loss of generality take to be equal to 1, then the rule of Pj into Fjx can be written as log of Pj Fjx, and we can write this out as log of Pj plus constant minus half of log sigma j minus half of x minus mu j prime sigma j inverse x minus mu j. And if we look at the minimum TPM rule, what we now have is this djx is log of Pj minus half of log sigma j minus half of x minus pj prime sigma j inverse x minus pj. And what we have done is we have discarded the constant term because it does not come into the rule, it negates each other out. And you can see that this function is a quadratic function in x, and therefore we call it a quadratic discriminant function. And then as before, we allocate gk to the gkth class if dkx is greater than djx for all j not equal to k. So that would be the minimum TPM rule. If the parameters are unknown, we replace them by the corresponding statistics to get the djx function as the same function replaced by the corresponding sample mean and the sample variance covariance matrix. Now let us take a very special case of normal populations when the variances are all same, that is sigma j is equal to sigma for all j equal to r. And if you look at log of Pj into Fjx now, you will see that this simplifies further because the sigmas are same. And of the 4 terms on the right hand side, the first is log Pj, the second is a constant, now the third is also a constant, and the fourth again depends on j. So we can discard the second and the third terms and just keep the first and the fourth terms, so that we have djx simplified as log of pj into the fourth term, which again simplifies to something like mu j prime sigma inverse xj minus half mu j prime sigma inverse mu j. And now you can see that the discriminating function is linear in the xj's. So, we have a linear discriminant function on which the decision rule is based. For unknown parameters again, the sigma and the mu j's can be replaced by their sample versions. So, we have mu j's replaced by the corresponding sample means xj bars and the sigma replaced by the pooled variance S. In today's lecture, we have looked at the classification rule for several populations. So, how do you classify an individual when there are more than two populations? Now, in this we have looked at the expected cost of misclassification as well as the simpler version of the total probability of misclassification. We have also looked at the apparent error rate, which is a performance measure by which we can judge whether the rule that we do is good enough or not. We have extended the results for the normal distribution. So, what we have done is we have extended what we have learnt in the earlier classes for two populations to several populations in this case.